Okay, so we're about to look at an example of something called the banked curve. Before we do that, we're going to do a quick review of grade 11, where we looked at a box on an inclined plane. The main reason we want to do this is because we need to understand how normal force works when the surface is not flat. So originally, when we looked at a car that's making a turn, we saw that it was basically just the force of friction that's keeping it along that circular path. So the reason why banked curves are important is because not only is it going to be friction that's helping us stay along this this turn, gravity will also help us out in making this turn. Where you might see banked curves, if, for example, if you're getting off a highway, lots of times those turns will be slightly banked, and usually it's whenever things are going really, really fast. Can't remember what it's called, but then in the Olympics, there's that Summer Olympics where that biking event where it's in that big oval loop and the bikes are going around and around and around circles, and it's super banked the sides. Yeah, it allows you to go really fast around a turn without basically slip and sliding. So let's do this question here. First, going to look at the grade 11 stuff first. And there we go. A box slides down a ramp that is inclined at 30 degrees. So when we saw this question in grade 11, again, hopefully you've covered it. First step when doing any force question is draw the free body diagram. We know force of gravity is down. That's our force of gravity vector. And the only other, at least when there's no friction, the only other force acting on this thing is what's called the normal force. And the normal force is it's basically the surface force. It's the force that prevents us from falling through whatever surface we're on. So it's holding up the object. And it's always perpendicular to the surface. So since our surface is angled like so, our normal force is actually angled. It's a very interesting thing happens. Since these are the only two forces acting on it, what we can see is that if we draw a triangle for force of gravity has to be the hypotenuse itself. A component of gravity cannot be bigger, so I'm going to draw a triangle like so, where this is 90 degrees. What we find out is we do a little geometry. This is 30 degrees right here. We find out this is FGX and FGY. So what you saw in grade 11 is instead of thinking of our regular coordinate axes as horizontal and vertical, what we do is we rotate our axes so that the x is parallel to the plane and the y is perpendicular to the plane. This basically simplifies our math. So what we can see here is, okay, so this thing is going to be coming and sliding down the ramp. So we know our net force, F net, is equal to the sum of the forces. So the key ideas from grade 11. So we know that this F net, that's equal to ma. That's going to describe our acceleration in the system. And then we have to write down all the individual forces acting on it. And if there was friction, friction always opposes the motion. So if you have this box on this incline, we have to ask yourself what wants to happen to this box. The box wants to slide downwards. It's going to oppose that. So if there was friction, it would be in this direction. So we see that, okay, if I say down the ramp is positive, I'd say the force of gravity in the x direction, that x component, it's kind of like the driving force. It's making it go accelerate downwards. And then it'd be minus the force of friction, which is opposing that acceleration. So we end up with ma is equal to mg is our force of gravity, but we need that x component, so that's going to be sine 30 based on our triangle. And our force of friction is equal to the coefficient times our normal force. We see our normal force is pointing up here, but there's the only forces in this y direction is normal force plus FGY. So force of friction is actually equal to mu FGY. But FGY is just the cos component, so it's going to be mu mg cos 30 degrees. And when there's no external forces acting on an object, we all notice that masses cancel out. So we get acceleration is equal to g sine 30 minus mu g cos 30. So the first one says if what is the acceleration if friction is 0? Pretty straightforward. That mu g cos 30 thing just becomes 0, so you get acceleration is equal to, so when mu is equal to 0, we get a is equal to 9.81, assuming we're on Earth, times sine 30, and we get 4.91 meters per second squared. And if the coefficient is 0.200, we get our acceleration is equal to, we get 9.81 sine 30 minus 0.2 times 9.81 times cos 30. And we get a value that is slightly smaller, so 3.21 meters per second squared. This makes sense. Again, friction is always going to make the acceleration less. Now this next example down below says what must the coefficient of static friction be equal to such that the box will remain stationary on the incline. So if I draw this out, I have this box on this incline. Force of gravity is downwards, normal force is this direction, force of friction is that direction. Basically what it comes down to, if we think about the x direction, this is the equation we just derived above. A is g sine 30 degrees minus mu g cos 30 degrees. If it's stationary, it means a is 0. So we're basically solving for when mu g cos 30 is equal to g sine 30. You see our g's cancel out. We can divide both sides by cos. So you get sine 30 over cos 30. And some of you may recognize this is a trigonometric identity, which is this becomes tan 30. So just plug in tan 30. And we get a coefficient of 0.577. So if the coefficient of static friction is 0.577, this thing would not slide.